Hi, this is an example problem from Chapter 22 about transformers. Pause for a moment and read the question. Okay, so we've got a problem here, and we've got a picture, and it shows a power plant. The power plant is generating a voltage here via Faraday's law, rotating a coil of wire through a magnetic field. The voltage is 400 volts, and then there's a step-up transformer here. It's going to step the voltage up to a value of 240,000 volts, and that's going to be transmitted through the transmission line over to a rural area. Now, in this problem, we're asked in part A, determine the percentage of power lost in the transmission line. Well, this is a two-step problem, so the first thing we want to do is figure out what happens when we step the voltage up. So here's our step-up transformer, and the side by the power plant is what we're going to call the primary. And the other side is what we're going to call the secondary. So the secondary is the power lines, in other words. Now, we're going to use the equation for a transformer to be able to relate the power, the voltage, and the current in the primary and the secondary of the transformer. So let's go ahead and write down for the primary. This is what we have. We've got the voltage in the primary equal to 4,000 volts. And we've got the current in the primary. It's equal to 100 amps. From this information, we are able to calculate the power in the primary. Remember that electrical power is equal to V times I. So in the primary, we can write it like this. Now I want to remind you that when we're dealing with transformers, the voltage, the current, these are all RMS values. We're not going to bother writing RMS as subscripts on any of these things, but this is the average power, this is the RMS current, the RMS voltage. So if we plug these two things in, we can calculate the power produced at the power plant. And we're going to get a value here. Four times 10 to the fifth watts. All right. Now in the secondary, so the transmission wires, we have Vs, and that's given 240,000 volts. So we're stepping it up. That's why it's a step-up transformer. The current in the secondary, we don't know what that is. However, we do know what the power in the secondary is. We're going to assume this is an ideal transformer. And in the transforming process, where we transfer the power from the power plant to the transmission lines, if it's an ideal transformer, then the power in the secondary is equal to the power in the primary. And in this class, we're going to assume that that's always the case for transformers. In reality, it's usually about 99% efficiency, so it's pretty good. So using this equation where the two powers are the same, we're going to be able to now figure out what the power in the secondary, the current in the secondary is equal to, right? So the power in the secondary, that is equal to the current in the secondary times the voltage in the secondary. And to solve for the current in the secondary, just do a little bit of algebra. That's going to be equal to the power divided by the voltage. And so we're going to put in 4 times 10 to the 5th watts divided by this big number, 240,000 volts. And that comes out to a small current of 1.667 amps. Now I want to go back and look at the problem again here. And notice that it says, don't confuse the power transferred in the transformer with the power dissipated in the resistance of the transmission lines. This, in other words, right? So what we're going to look at now is, in order for the electrical energy, the power, to be transmitted all the way along these power lines over to the rural area, the current is going to be flowing in those transmission lines, and because of that, some of that power is lost. Some of the power is going to be lost as heating of those transmission wires. And so when we're going to be looking at the heating of the transmission wires, we have to be sure that we use the equation for the power dissipated by a resistor. And so there it is. So this is the power lost because it's dissipated in the resistor. We calculate that as the current in the transmission wires, that's the secondary, squared multiplied by the resistance, the effective resistance of the transmission wires, R. Now the current that we just calculated, 1.667 amps, and the effective resistance of the power line, so collectively throughout the entire transmission lines, we've got 30 ohms. Putting that into the calculator, we get a value that is equal to 83.3 watts. Okay, now so for part A, to calculate the percentage of power lost in transmission, we're going to go ahead and take the ratio here. So the power lost divided by the total power that we started with at the generator. So I'll write primary, multiplied by 100%, which comes out to 83.3 watts divided by 4 times 10 to the 5th watts. Of course, the watts will cancel here. Multiplied by 100%, and that comes out to 0.020%. So it's a very small amount of power that's lost in transmission. Now, let's see what the case would be if we didn't use the transformer. If we didn't use the transformer, then we would have the large current, 400 amps, that would need to go through the transmission wires. Let's calculate how much power is lost if we have that high of a current. Notice that the current is squared, and that makes the current hugely impactful in terms of the power that is dissipated and lost in the transmission lines. So if we go ahead and just put in our numbers, 400 amps, square that, times the resistance in the wires, that comes to a value of 300,000 watts, or this is 3 times 10 to the 5th watts. That's a huge amount of power lost. And if we go ahead and calculate the ratio again, we need to replace this number with this number. Well, this one you can actually do in your head because this stuff's going to cancel out. And 3/4 is 0.75 times 100% gives us a ratio of 75%. So in this case, we lost 75% of the power generated at the plant due to heating of the transmission lines. This is why Tesla won the battle versus Edison on whether we should use DC current or AC current for powering an electrical grid. You can see that if it was direct current, there's no way for a transformer to step it up and lower the current. Therefore, you'd have huge losses. And so that was Tesla's genius in promoting AC circuits and AC current.